Hey guys, this is one for the mechanical engineers out there trying to get through their degree at the moment. You'll probably find it difficult to find stuff on YouTube directly answering questions like this and problems like this. So we've got to determine the acceleration of a piston inside a cylinder. So here's your piston up here inside the cylinder. Trying to find out how quickly it's accelerating. We don't know whether it's moving up or down at the moment. All we know is we have some angular accelerations of link AB and some angular velocities of link AB and also link BC, just given here. Also, we will be using cross products, but we'll get to that during the question. And if you're not too sure, maybe the symbols you use are different to denote angular acceleration and velocity, but just take note of them down here. Maybe it's different in your country, but these are what we use in Australia. So let's get into it. Basically what we're going to do is we're going to analyse link AB and then we're going to analyse link BC. So we have the formula for the acceleration at B up here and also the acceleration at C. So let's analyse link AB. So we use the formula at the top there, have AB is equal to the acceleration at point A. Now it's locked into a pin here, so there's no acceleration down there. That's straightforward, that's 0. Plus the angular acceleration AB. So we have 20 radians per second squared. Just note, this is in the clockwise direction. I'm sure you remember from summing moments and things like that, that clockwise indicates negative, anti-clockwise indicates positive. So this is actually a negative 20 radians per second. So I'll make that negative 20. And the angular acceleration is actually rotating around your K axis. So because I need to break this up into I, J, and K components, this is important. It's rotating around your K axis, which is going into the page for you, into the screen for you. So denote that with a K. Important to keep track of your I, J, and K components. So this is then the cross product of the radius of B with respect to A. So how we do this is we basically got to break it up into I and J components. So if this is our link, pretty simple trick, this is our link AB. This would be our J component of it. Important to note that's in the positive direction. And this would be our I component. Now that's in the negative direction. Also important to note that. So we have 45 degrees in there. So always, your J components are always going to have a cos in front of them, okay? So this length here is 0.25 meters, so I won't go through the trig. Very simple, it's 0.25 cos 45. Now, let me just write this out for you actually. This is important to note. Normally you would write cos 45 equals the adjacent over the hypotenuse, which is J over 0.25, and therefore this component just equals 0.25 cos 45. You would normally just write that straight in, but we need to track the I and J components, so make sure you put J next to it. Critical you do that. Now we've got a negative I component. This will just be the same, except it will be sine 45 of I. So just note where I got the negative from there. It's because the I component is going in the negative I direction. That's why it's negative. So that's that, and then we have minus the angular velocity at AB, which is 10 radians per second, 10 squared, times, just note that R at B of A and R at B of A, these will be the exact same. So that will go there, and that will go there. Those are the exact same. So then all we need to do is just pull these together. So you're going to end up with okay, so let's go through the cross product part first. So you have minus 20 K cross product with J. Now here's where we're going to use this little trick over here. So Kj equals minus I have here. So when you go back around the circle, K to J equals I, it's a negative answer. If you came forward, Ij equals K, as you can see from here. When you're going clockwise with it, it's always positive. When you go anti-clockwise, you're getting negative component answers. So in our case, we've got Kj, and always keep the order. Don't say JK, it's KJ. So kj is equal to minus I. So because we already have a negative here, it becomes a positive. That will end up being minus 20k. Actually ends up being 3.54 I once you multiply that out. 20 times 0.25 cos 45. And then this time we have k into I. So ki, what does that equal? Ki equals j. But because we have negative and negative as well, the negatives are going to cancel each other out. So this is also positive. If you don't believe me, you can get your calculator out and multiply those out. That's what it'll end up being. And over here, we're having 10 squared into what we had on this side. That will equal minus 17.68 j plus 17.68i. And if we sum these together, we have AB equals 21.2i minus 14.14j. And these are accelerations meters per second squared. So that's link AB. So that's our I and J components of what's happening at point B for the acceleration. So now we go to link BC. Our orange link here. So we're using the formula up here. So we have AC equals acceleration at B, which we've just worked out. 21.2i minus 14.14j plus our angular acceleration at BC, which we don't know yet. This is what we're trying to find out, so that's something we don't have. So angular acceleration at BC. Note again, angular acceleration is in the k vector component as it rotates around the k-axis. Make sure you have k with that to cross product. And again, this is pretty simple trig. So we have our link BC, we have our J component, which is positive, and our I component, which is also positive this time. So we have 13.6 degrees up in that point there, and we know this length is 0.75 from the question. So therefore, just noting again, your I components always come out as sine, always. So this is 0.75 sine 13.6. Make sure you can put your component in there as well, your I component, plus 0.75 cos 13.6 of your J component. Still going with this equation, still got this part of it to do, minus our angular velocity at BC, which is 2.43 squared times, remember, these are always the same. This part plus this part, it's always the same. You get used to that, it's pretty easy. So once we have that and we add all these together, one other important point to notice here is the acceleration at C is purely in the J component direction. It cannot move horizontally in the I because it's jammed in the cylinder basically. It's inside the cylinder. It's only moving in the J direction, which makes this a J component. So acceleration of point C is a J component. And once we add all these together, we end up with 21.21 I minus 14.14 J plus 0.177 angular acceleration at BC of J minus 0.729 angular acceleration at BC of I. Still going, minus 1.04 I minus 4.3 J. So that's all up what you have. Now I will run you through this just quickly again. The cross product part of it, make sure the KI, so look, what do you got for KI? KI equals J, that's why it comes out as J here, that part of the cross product. The next part is KJ. When you look at KJ, you get minus I. That's why it comes out as an I cross product and also the negative because it's the minus I. That's it. So once we add these together, well, we're not going to actually add them together yet. What we're going to do now is break them up into their I and j components. So what we can do is, we'll take firstly all the I components out of this equation. So we have, on this side of the equation, we have no I components. So we have 0, we only have the j component on the left-hand side of the equation. Let's just put an I over here, so we're going to do I components. Equals 21.21i. Where's the next I? Minus 0.729 alpha BC of I. Minus 1.04i. So there's all our I components, and this is equation 1. Now we'll get our j components. So on the left side of the equation we have the acceleration at c, which is obviously the j component. So this is why it was important to note and recognize that this is a purely j component. So on the right hand side of the equation we have minus 14.14 j plus 0.177 alpha BCJ minus 4.3j. And that's equation 2. Now, in equation 2, we have 2 unknowns, so you can't solve it. But in equation 1, as you can see, we have alpha BC on its own, so we can solve for that. Alpha BC therefore comes out at 27.7 radians per second squared. Now, if you've gotten this far in engineering, I'm pretty sure you know how to solve this now for the acceleration at c, which is your answer. I'm simply going to put my value for ABC in here and sum this up, and you get an answer out at minus 13.5 meters per second squared. So that indicates that the piston is accelerating, and it's accelerating down 13.5 meters per second squared.